Today we're going to continue our discussion of symmetries, space-time symmetry transformations and representations in field theory. This is going to be the last lecture where we discuss classical field theory. I already, like the second half of the lecture already starts talking about quantum, and the remainder of the course is going to be quantization. We're going to be quantizing that. So I've walked you guys through a lot of representation theory and classical field theory, and we're ready as of to start quantizing the theory as of the next lecture. But for now, this is what we're going to say in this lecture is sort of the punchline that I've had promised for a while now, that the irreducible unitary representations of the Poincare group are going to be one particle states. So they're going to be the interpretation of what a particle is in field theory. And actually here we're going to say that that is where the word quantum is. All right. Let's start, because it's been a week. Let's start with a review of what we discussed in the last lecture. So spinors. We said that spinors correspond to projective representation of Lorentz group. We said that we're interested in restricted Lorentz group, SOD plus 1. That is the part of the Lorentz group that's continuously connected to the identity operator. And the projective representations correspond to, there's this double cover, spin plus d comma 1. All right, so the Lie algebra of the Euclidean theory, which is SO4 in 3 plus 1 dimensions, we said that is spin 4. This is 2 copies of SU2 Lie algebra, right? So these are the standard relations of SU2. And we said that if you form the following combination, these generators, from the boost and rotations, so rotations are Ji and Ki are boosts, you explicitly realize what these SU2 two copies of SU2 are. So this is not a terribly abstract concept. It's just a complex sum of boost and generators of boost and rotations. All right. Then we said, because we're interested in irreducible representations, this representation theory is very familiar to you guys already, because it's SU2, so there are like J left and J right. Each J is a spin index, right? And you're going to have a whole bunch of representations. The simplest one is a 0, 0, 0, comma 0. This is a scalar field. Then there's half 0. This is the left wild spinner, 0 half. That is a right wild spinner. And because we're talking about SO4, Euclidean theory, this representation theory is a representation of, these are independent real spinners, right? Then we mentioned that, okay, so that was the Euclidean theory. We're interested in Lorentzian theory, so it's a little bit subtle. What we're interested in is SO3, comma 1 and not SO4. And in this case, the spin group is SL2C. What that implies, if you are not interested in the group theory side of it, is that this left and right wild spinners that you found, they are going to be no longer independent real spinners. What you're going to have is a left spinner, you're going to have a complex spinner. So these variables psi1 and psi2 are now complex, but it comes, of course, the total number of degrees of freedom is conserved. It comes at the cost of the right movers being the dagger, the adjoint of the left movers. Right? Any questions? All right. Then we, in our quest to construct representation theory Lorentz group, we said that what we did was that we constructed 4x4 Dirac matrices. This whole story is specialized to 3 plus 1 dimensions, okay? But it generalizes. We're not discussing the generalization here. These Dirac matrices, there are 4 of them, right? So each of them is 4x4, and there's 4 of them, for mu index runs from 0 to 4, right? 0 to 3, 0, 1, 2, 3. They satisfy the Clifford algebra. These are the anti-commutation relations. And to just see directly how it's related to representations of the Lorentz group, the commutator of two of these Dirac matrices multiplied by I/4 is this sigma tilde, which is the generator of the Lorentz transformation. So exponentiated, these do become Lorentz transformation, right? So these are 4x4 representations. Sorry, these are 4-dimensional representations, right? Because we started by 4x4 matrices, Dirac matrices. So the most natural thing to consider is the Dirac spinner, which is a 4-component vector. And it's natural, based on our discussion of the previous discussion, to split it into, in the chiral basis, split it into 2 upper components and 2 lower components. If this were a massless Dirac fermion, these would have been wild fermions, right? So this is how we show them as I've written it. Okay, so chi and that's chi. Yeah, chi and chi bar are independent, right? So there are 4 independent complex variables. The Dirac equation, the equation of motion that this guy satisfies, is this equation, right? And this M prime is the Dirac mass. We also introduced Majorana spinners. Majorana spinners were the ones that the upper and lower components were the dagger of each other, right? And then we also introduced Weil spinners, which are found by just projecting to the left movers and right movers. So these are all the spinners that we ever want to talk about, right? All right. So today, we're going to talk about how elementary particles, few words here, are elementary particles, are unitary, sorry about that, are unitary EREPs of the Poincare group, and then we're going to discuss solutions of the free Dirac equation, right? So we for the scalar field, we saw the Klein-Gordon field. We had the Klein-Gordon equation, and then we solved it. It was just pretty straightforward. It was easy to write it down in terms of the plane waves with an unshelled condition, if you recall. There was plane waves with an unshelled condition. We're going to do a similar analysis for Dirac fermions. All right. Any questions? Good. So what is an elementary particle? I'll try to take a very intuitive point of view. You'll stop me if there's something that's ambiguous or unclear. Consider a vector. So now immediately I'm talking about quantum, right? So we said that when we're talking about representation theory, vectors in the Hilbert space, right? Sorry, the symmetry group should always be a unitary or anti-unitary representation in the Hilbert space. Should be represented. This was Wigner's theorem, right? And maybe I didn't say it at the time, but the anti-unitary in physics almost always, one way or another, is related to time reversal. So if you're not dealing with time reversal, basically all of your symmetry groups are unitary transformation, right? So now consider a vector in the Hilbert space. There's this quantum field theory Hilbert space. We haven't constructed it yet, but there will be a vector that will deserve to be called one particle state, describing it's a wave function. Of course, it's a state, right? In a quantum theory, it's a wave function that describes a single particle of type alpha and mass m alpha. I will just usually say m at rest, right? So there is a vector in the Hilbert space that describes such a state. So an empty universe with only a single particle at rest. There is no canonical meaning to where that particle is, right? Do you guys know why? Why is there no physical meaning associated with where the particle is? because if this is only a single particle sitting on top of vacuum, vacuum is translation invariant, right? So that's just a choice of redundancy that it could introduced. All right. Good. So this is a vector. Now, what we're going to do as a strategy to decide what is the meaning of a single particle is to say, okay, so this is, somebody told me that there's a vector in the Hilbert space that is describing the state, and I'm going to call that a single particle vector. Now, I'm going to include all the other states that I would say is the same, are describing the same particle. In particular, if you take this state and apply a Poincare transformation, for example, boost it or translate or do anything of that type, it might or might not change the state, but it won't matter. Any Poincare transformation acting on this, you would still want to call that a single particle state, right? That's just a very natural thing to do. So therefore, we just conclude that, so you would say it's the same particle. So you conclude that a particle in quantum field theory is a subspace of the Hilbert space, is a set of vectors in the Hilbert space that transform as a unitary representation of the Poincare group. Why unitary representation? Because we are talking about the action of the Poincare group in the Hilbert space, and by Wigner's theorem, it has to be unitary representation. So it's some sort of subspace V alpha. Alpha is the label of the particle, right? That describes the motion of this guy. You know, the state might change under the action of Poincare transformation, but you would still call all the states in this subspace, you would still call them a single particle. That particular single particle. Now, let's say you take two such subspaces corresponding to alpha and beta particles and direct sum them. This is still a unitary representation. The physical picture, cartoon to have in mind, is that if in the previous picture you had an alpha particle that was moving in space and getting boosted and all that, this is like a state. It's a composite state that has alpha and beta don't talk to each other, right? And this is still representation, but you wouldn't want to call this an elementary particle. You would want to call this a composite state made out of two particles. Why? Because under Poincare transformations, type alpha particles never become type beta particles. So the representation splits into two parts. And the Poincare transformation rotates at one part within itself, this part within itself, this part within itself. This resonates pretty clearly with the idea of irreducible representation, right? Irreducible representation is a representation where you cannot do this. So state that transform a representation that could not be split into subparts, sub-representation is an irreducible representation that deserves to be called an elementary particle. So an elementary particle is a unitary irreducible representation of the Poincare group. That's the only meaning associated with a particle in quantum field theory. So based on that, I'm going to walk you guys through a little bit more representation theory. It won't be too crazy. But why do I want to do that? Because now the question of what kind of irreducible representations exist is a question of what kind of classifying all possible particles that could exist in flat space. It's a very physical question. This whole thing was Wigner's baby. Wigner really did all of this. All right, any questions? This was a little bit perhaps quick. I'll try to build intuition by giving an example from quantum mechanics. All right, so let's forget about relativity for a second, because the principle I'm describing is more general. Let's talk about a non-relativistic particle, good old quantum mechanics. So you have a one particle, you're describing a single particle and you're quantizing a single particle. So what did that mean in sorry, what's the translation of what we used to do in quantum mechanics to this modern language? We constructed a one particle Hilbert space by solving the Schrodinger equation. Let's say we're just looking at like states that are time independent, right? So we wanted a free particle. Here's the Schrodinger equation. The solution to this Schrodinger equation are basically plane waves, right? Let's say I'm in one dimension, right? And the energy is basically set to be p squared over 2f, right? By the way, this is very similar. The analysis of, in your head, you can just put this right next to Klein-Gordon equation, right? So that will be a direct generalization of it. Now, the one particle states is the Hilbert space of square integrable vectors of these psi p's, right? Because each of these, so these guys form an orthonormal basis. Well, they're actually delta function normalizable, but anyway, right? So these guys are the things that we call p hats. So a state in the Hilbert space that describes an arbitrary state that describes a single particle is a square integrable wave function psi of p. Square integrable means that you just take a measure dp and integrate psi squared and you get 1. This is the Hilbert space of interest, right? Hopefully that is familiar. Now, if you had an internal symmetry group, like a conserved charge, this is still quantum mechanics, right? This is still quantum mechanics. That single particle had some sort of conserved charge. There was a symmetry group G. Then by Wigner's theorem, that symmetry group should be represented as a unitary on the Hilbert space. And because it's internal, this p hat is left invariant under the action of this guy, right? So in that case, what is the interpretation of a single particle? Hilbert space is the wave functionals that transform in the following way. There are two parts of the wave function. There's a part that is space, right? And that is described this way by square integrable functions psi p. And then there's a part that has to do with the internal symmetries. And that is, by Wigner's theorem, it has to be about unitary EREFs of G, right? This principle is going to be the main guiding principle when we construct representations of Poincare group. But the key point being this. What did we do? We first looked at these we looked at a particle, then we start acting with space transformations, right? That helped us span a whole Hilbert space. These are square integrable functions of momentum. Then we said, okay, there is a part of the story, there is a part of the set of transformation in the Hilbert space that leave your momentum invariant, unchanged. Then your state has to also transform under an EREF of that. Right? Is the principle clear? Because the Poincare representation theory is a direct generalization of this. Okay. Now, maybe I should pause. Any questions? All right. Now, let's talk about particle states and classifying unitary irreducible representations of the Poincare group. That's our task. So let's recall what the Poincare group is. It's SOD comma 1, that is the Lorentz part, and then there is this semi-direct part, translations, right? It's sometimes called inhomogeneous Lorentz group. You sometimes see notation like ISOD comma 1 or something like that. I don't like that notation. I will avoid it. But if you see that in a textbook, that's what it is. Inhomogeneous Lorentz group. The principle that we just saw applies here. First, so there will be, first we focus on the translation group. right? Like before. And we're going to end up with a set of functions that are square integrable functions of momenta. So then we're going to look at the subgroup of Lorentz transformations that leave the momentum for vector invariant. That's the analog of this internal in this picture, right? That subgroup has a name. It's called little group. So the state will transform. The representation will be, there will be two parts to it. One part is going to be just the momentum, square integral functions of momentum with an extra unshelled constraint. And there will be the part that has to do with an irreducible unitary representation of the little group. The little group is just the part of the Lorentz group that leaves this momentum for vector in there. We'll see that. So let's focus on step one, which is these translations. So there's a translation subgroup. Hopefully the representation theory of that is pretty obvious. It's just e to the power of I, A mu, P mu. P mu is a, so these are translations by A mu. P mu is a self-adjoint operator because you want a representation that is unitary. Right? Okay. So I'm not very consistent with my hats. It's like it's implied what is an operator, what's not an operator. So now here's a state. You could label your states as the eigen operators of this four momentum vector, the same way that we did in the other example. This is like e to the power of I xp, right? Kind of set up. And yeah, so they transform. This is how translations act on these eigenstates of momentum operator. These are one particle states, right? Good. All right. Now we notice that Lorentz group acting. So the Lorentz group and the translation do not commute. So their story is a little bit more complicated than the previous part. If you take a translation and act with Lorentz transformations, sandwich of Lorentz transformation on both sides, what you're going to do is that you're going to you're going to Lorentz transform the translation, right? So what does that mean? It means that the same way that we, in the past, we integrated along all the momenta, here, you're going to integrate over. So you start with a particle, let's say at rest. Under Lorentz transformations, it's you're gonna generate the four momentum, right? But not any four momentum. You will generate all four momenta that satisfy this constraint, unshelled constraint, right? So there are two constraints here actually. One is the unshelled constraint. If you look at this unshelled constraint in the space of four momentum space, there will be P0 and other P's. This corresponds to two of these balls. And the upper one is positive frequency, the lower one is negative frequency. So we want positive frequency because we want positive energy, right? So what you will have to do is previously just integrated over P. Here you're going to integrate over P with these two conditions. The first Dirac delta function makes sure that you're unshelled because it's a massive particle of fixed mass, right? That constraint should always be satisfied. That's relativity. And the second one is a positive energy condition. Sorry, positivity of energy. Positive energy condition means something else, right? And you'll see that there is a way of rewriting this. You could do these integrals explicitly and get this form, but we'll come to that when we quantize the theory. So what do we end up with? The analog of those square integrable functions become functions that are square integrable next to this kernel. Because these are the set of allowed momenta. Right? Are we good? Such a thing is just a wave function for that particular particle of mass m. Right? So here there's an opportunity to tell you guys about another phenomenon in physics. Maybe if we have some extra time, we're left with some extra time, I'll come back and comment on it. But all right, is this part clear? Here, you could have actually treated this non-relativistic example as if it's relativistic, integrated over here where you integrated over dp, you could have integrated over dp0 being energy, dE, and dpx, and then put in this condition, on-shell condition. It wouldn't change. It would be the exact same. Nothing would change. All right. So far, what we're describing is that we start with a particular state in the Hilbert space that represented the particle at rest with mass m. Then we started Lorentz transforming it. That changed the form momentum, and we said, well, okay, you can just add up all these vectors. You can superpose them with arbitrary coefficients, and as long as the arbitrary coefficient you're superposing with is square integrable function, this is a legitimate wave function. Good? All right, so now let's get to the little group. The little group is the subgroup that leaves p mu, the 4-vector, invariant. Let's simplify our life and focus on the case where the state has mass and spin, and it's in its rest frame. So this is what the form momentum is. So in space-time, if I'm drawing the space-time structure of it, if the particle is addressed at a particular point, right? It's just a world line sitting at a particular point. What set of Poincare transformations leave this guy invariant? Well, rotations, right? Rotations around that point where the particle is sitting, right? So in this case, the little group is just space rotations. That's it. These are the set of transformations that leave your 4-vector invariant, right? So if you want to construct, if you want to construct, I want to remind you guys, if you want to construct the EREPs of Poincare group, there will be 2 parts of the story. A unitary EREP of the little group and the square integral function on the orbit of p mu. Orbit of the p mu is this thing. Now, little group, of course, I give you an example of the little group when the p mu is, the particle is in its rest frame, right? But if the particle is moving with some form momentum, you're in a frame where form momentum is non-zero, right? The little group would be rotations in this rest frame, Lorentz transform to whatever the frame you are in, right? Any questions? Hopefully these are intuitive. These should not be too abstract. All right. So one thing that's important here is that there are EREPs of Poincare group will crucially depend on whether you have mass or not. Up to here, I pretend that they have a non-zero mass, right? So these are the case of massive particles, and I'm taking the mass to be positive, right? So let's go through this in a little bit more detail. Then I will treat the massless case separately, and you'll see the distinction. So recall that, for example, if you have a spin 1 particle that's massive, you should end up with a representation theory that has 3 polarizations. Whereas if you have a massless mode, you should end up with a representation theory with 2 polarization. The transfers should be redundant. right? This is hopefully something to remember from our discussion earlier. All right, when you have a massive particle, you do have a rest frame. So as I said, the low group is the rotation subgroup that leaves this vector invariant in this rest frame. So basically you transform as an irrep of SO3 and with the score integrable function over momenta, on shell momenta, right? Now, what's the representation theory of SO3? These are just rotations, right? These are hopefully something you remember from quantum mechanics, right? But in principle, they also have spinors, and because there are we are talking about vectors in the Hilbert space, so you could have spinors that they correspond to projective representations, and that will be crucial actually, right? All right. So how is this related to the spinor representation of the full Poincare group? Here we're talking about spinor representations or projective representations of a particular subgroup, spatial rotations. So let's see how this little group sits inside the full Poincare group. Oh, sorry, Lorentz group. I said Poincare, Lorentz group. So remember that Lorentz 4-vector P mu could be written in terms of the spinor indices, left and right spinor indices. It's the transform as a half comma half, right? That's the transformation. And this is explicitly what it looks like if you write a 4-vector in the mass, in the rest frame, in terms of a representation, spinor representation. So it's a 2x2 matrix with M on the diagonals. This is the formula that we use. All right, how does this transform? It will transform like a representation of the left spinor on the left and a representation of the right spinor on the right, right? So in general, you have two of these guys. This is something that I might give you as a homework problem. But so there is a generator of the left transformations and generators of the right transformations. You could add them up. This is a diagonal component. Turns out that it's this diagonal component that leaves this guy invariant. Right? When we say that we have two copies of SU2, it means that on this vector, you could act on the left however you wish and on the right however you wish, right? But then there's a diagonal subgroup of that, that is actually generated by JL and JR adding them together. This diagonal subgroup is nothing but rotation. In the case of this rest frame, it's just a little, I guess, exercise to work out in detail. So what's the other set of generators that are left? Well, next to adding them, you could subtract them. These guys generate boosts, actually. These are the non-trivial boosts that will change your P mu. Right? So the little group, you identify it as the SU2 generated by adding the generators this way. Hopefully it's clear that it will generate SU2. It's a diagonal. So in summary, I first described why these rotations do nothing, because if P mu is nothing is happening to P mu, right? You're in the rest frame, is 0, the vector is 0, right? And then this is the same thing described in the spinor representations. It's the diagonal part. It's the SU2 generated by the diagonal part of the SU2 left, SU2 right. All right, so very good. So if you want a one particle representation, you're going to have a mass, right? That mass fixes for you the unshell condition. You can integrate, as I said, with the score integrable function over p's that satisfy that unshell condition, some positive energy thing. And this J and J3 are now the representations of the diagonal SU2, the little group. Okay. Very good. I was gonna ask, I guess this is repetitive. Just think about it. It's something to think about. Why couldn't we use E-reps of independent left and independent right? Why couldn't we use Lorentz? Well, the simple answer is that under Poincare transformations, that you will go from left inverse to right inverse. All right. So now boosted states are found by applying these boost transformations, the other part of these Lorentz transformations, right? And then this is the guy that pushes you along this this thing, moves you around this, right? Very good. So that was the story of the massless particle, massive particle, right? This is the full representation theory. And that is what deserves to be called a particle, an elementary particle. Now, there's a catch. Well, something for you guys to think about. If there are bound states, does this formalism treat bound states the same as elementary particles or not? So something to think about. All right. Any questions? In summary, we said that elementary particles are irreducible unitary representations of the Poincare group. We said if you want to do that, if you want to construct such representations, it's a two-step process. First, you look at wave functions. Your particle has a mass, right? So there's an unshelled condition. So you have this p mu equal m squared, right? You first integrate over with a square integrable function over that space. Then you look at that E-rep of the parts of the Lorentz group that preserves, that leaves your p mu invariant, right? That's like internal in this, from the point of view of this integration, right? There's a long story associated with this in group theory, but it's a very standard formalism, induced representations. But anyway, we use them all over the place in physics. But yeah, so that this little group is, in the case of rest frame, is just rotations, right? And you need an E-rep of that, and then you're good to go. That's what the particle is. Okay, what if the particle is massless? Well, if you have a massless particle, you don't have a rest frame. There's no such a thing as a rest frame, but you could always put the vector p mu in the following canonical form, right? So you basically make the spatial component of your 4 vector to be along, like, let's say the x1, p1, sorry, p1, right? Now you could ask, what is the little group? The little group is just a little homework to figure it out. It's generated by these 3 components of Lorentz group. Hopefully, it's obvious that J1 is in there, because J1 generates a rotation in the 2-3 plane, and it's a symmetry. It doesn't do anything here. The part that's a little bit non-trivial are these 2 generators. But if you want to work out to see why are these 2 generators leaving, these are weird combinations of boosts and rotations and other in different directions. If you want to work out to check to see, and these guys are going to leave the vector invariant, well, the simplest way to do it is just take the representation of a Lorentz group that we discussed, right, in terms of these 4x4 matrices, and it turns out that it's this guy that preserves your p mu that's in this form. All right. Good. Is the principle clear? Is the idea clear? I don't have an intuition for this topic. It's not, I don't have a geometric intuition. Maybe some people do, I do not. but it's hopefully clear. We could be very explicit about the generators. All right, so here are the three generators. J1 is convenient to pack them. Well, no, this is what they are. They satisfy the following algebra. This is not SU2. Previously, right, it was SO3 rotations, which was the same Lie algebra as SU2. Here, you get something different. You get something that looks like actually itself is actually a two-dimensional, it's an isometry group of R2, two-dimensional flat space. These correspond to translations, so Euclidean two-dimensional space. These correspond to translations in the Euclidean P1 and P2 directions, and this guy is rotation, generator rotation. But again, this is an abstract space. This is a completely abstract space. Right? There's no, this is not nicely related to real space-time. All right. So if you want to construct a representation theory of this, it's a very systematic representation theory you could do, but something funny happens. Well, actually, the representations that appear in physics are very, very simple, trivially simple. So in full generality, if you want to do this, you just construct this raising and lowering operators, A plus minus, from A and B. They commute, and then they satisfy this equation. That's why I call them raising and lowering operators. So you want to represent an irreducible unity representation of this. The set of representations that appear in physics, to my knowledge, this is all I've ever seen, it's a very, very simple representation. It's a set of representations such that the vectors are killed by both raising and lowering operators. So there is only just one lambda here. Whoops, sorry, I was planning on doing the full representation theory. I changed my mind. So. All right, turns out, this I haven't said, there is a symmetry of quantum field theory called CRT. CPT, actually, let's call it CPT, right? CPT, charge conjugation, parity, and time reversal is a symmetry. That will tell you that if you have lambda, you also must have minus lambda. And also, if you do the representation properly, I didn't really explain it, the values of lambda end up looking like this: 0 plus minus half, plus minus 1, and so on and so forth. The absolute value of this lambda is called spin for a massless particle. And the actual value of lambda is called helicity. So the representations are basically labeled in the following way. So if you have a photon is spin 1, so you have helicity plus 1, and then CPT, symmetry of quantum field theory, will tell you that you will have a helicity minus 1. So these are the two helicity states of massless photon that appear in physics. There is no lambda equals 0 for photon. Irreducible representations are just this way. Okay. Are we good? Any questions? I was very brief on this because I wanted to give it as a homework, a more general setup, but I can tell you in advance, it's a mathematical curiosity, to my knowledge. It doesn't appear in physics. The more general representations, they do not appear. Maybe they do in some exotic system. I'm not familiar with it. All right. Any questions? So this brings to an end our discussion of unitary irreps of Poincare group. For massive particles, if you want to understand how they work, is that there are one particle states are basically, there's always a square integrable function worth of momentum wave functional, And then there is an E-rep of the SU2, which is basically the little group, the part of the Lorentz, the subgroup of Lorentz that preserves your P mu vector, which is basically rotations in your rest frame. In the rest frame of the particle is always rotations. And that's it. And for massless particle, the representation theory is very, very simple, but the little group is a little bit more involved. It's fine because there's just no rest frame. And we end up with two helicities for massless particles. Good. Any questions? Because we're going to switch gears and talk about solution to the Dirac equation. All right.
How is the projective representation of the little group related to the projective representation of the Poincare ray group?
So, okay, very good. I identified the little group. So when I wrote this down, right? This includes both regular and projective representation, right? Because J left and J right could independently run from 0, half, 1, 3 halves, and so forth, right? So the half integer ones are any representation that has a half integer, either left or right, is a spinor, has a spinor component, it's projective, right? And then I constructed this diagonal bit. Of course, a diagonal bit could also include half integers, right? But it will depend on the left and right. So that is how they relate to each other. I embedded this subgroup, this spin group inside the spin 3, 1. Now there's a subtlety here that I actually sort of embedded the Euclidean one. Yeah, there are subtleties. We're not. It's not a course on group theory, and I also have to really look up the details of it. I don't know it off the top of my head, but yeah. Is the principle clear?
Yeah, thank you.
Sure. All right, solutions to the free Dirac equation. So this is the last discussion we're going to have for classical field theory, and it's in a sense already a little bit quantum because these are projective representations, right? But anyway, they're projective representations. They don't need to be quantum. All right, so here's our simplest Dirac equation, the simplest form of it. I'm replacing m prime by m. That's the Dirac mass. That's the only thing I deal with in this part of the course. So first thing to notice is that it's a first order differential equation. So it's unclear a priori that it has anything to do with waves, right? Waves appear naturally as a solution to the second order differential equation. Is that clear to everybody? Okay. Now, however, a simple trick tells you that you could take plane waves and expand solutions to these equations in the basis of plane waves. How? Well, you had this differential operator that was killing your function. Act with the same differential operator with the plus sign. You should still kill your psi. But now this is just a Klein-Gordon equation, right? The solutions. So this tells you that plane waves that were solutions to this guy will also provide a very nice basis for solutions to this guy. Solutions to the Dirac equation. Good. But keep in mind that this is a matrix equation, right? These gamma mu's are 4 by 4 matrices. The solution to this is a 4 vector. Good. All right. So if you recall from solutions to the Klein-Gordon, there were these like e2 minus I p mu x mu with this unshelled condition, and then we're going to pick p0 to be positive. right? So far, so good. Now I'm going to introduce these. I'm going to separate the part that has this vector structure in it separately. So these are 4 vectors. These are the internal spinner details, right? But I just motivated by the fact that the plane waves provide a basis. I'm just expanding my function this way. Good. So this is an ansatz that you plug in inside the Dirac equation, and you find that mu p and v of p will solve these 2 equations. So this is sometimes, I don't know what to call it. Let me call it positive mode, positive mass, whatever. This is like a positive energy mode. This is the solution to what we're, the solution to the equation we're trying to solve, right? For p mu. Whereas this one has the sign of mass flipped, right? But these are all, they're providing solution to this equation. All right, so because we want to simplify our lives, let's go sit in the rest frame. So the rest frame, this is a massive particle, massive spinner, so it's m and 0. This is your, so I'm going to treat these 2 equations separately, right? I'm first going to look at the positive mode. Because gamma 0 is the only non-zero Dirac matrix you have, because you're in the rest frame, this is your equation. And you could just take it out, it looks like this. Good. Maybe this notation is confusing. These are identities, right? These are 4 by 4. So each of those guys is 2 by 2. What's the solution to this? Is something that looks like this. This square root m outside is conventional. We put it there because so that this C dagger C is properly normalized. That's a conventional thing. But this is what it looks like. Each these C's are 2 vectors. They have upper and lower components, right? So remember that this is a vector with 4 components. So the upper spin one